Good morning, friends. I feel immense pleasure to be here again for my course Engineering Thermodynamics. As of now, I have completed my fourth module. Today, I am in module number 5th. The name of this module is Elements of Heat Transfer and Gas Compressors. So, this module I have divided into the two groups. One is the heat transfer, another is the gas compressors. So, in this module, I am going to take some 10 to 11 lectures. In these 11 lectures, we will have some 2 or 3 lectures for the numerical problems, and remaining will be the theoretical part, derivation and mathematical expression for the heat transfer and the gas compressors. Today's my topic is Introduction to Heat Transfer. In this, I am going to discuss about heat transfer part only and very basics about the heat transfer. In today's lecture, I am going to take Introduction to Heat Transfer, and in this I will be discussing about modes of heat transfer. And this modes of heat transfer, if you see, we have the conduction, convection and the radiation. So these 3 modes I am going to cover in this lecture. So before I start this thing, what we have done till now, just I will give the glance of this thing. If you see the module 1, module 2, module 3 and module 4, and we are here. We are here. So in the module 1, module 2, module 3 and the module 4, in module 4 we have seen the psychometry and the TS, HS diagram and psychrometry. We have taken few lectures on this, and if you talk about the module, this in module 3, sorry, here module 4 we have given the power cycle, and in this we have covered Otto cycle, diesel cycle, dual cycle. Then we have seen the Brayton cycle. Then we have seen the Bell-Coleman cycle. This we have covered. And in this we have covered the psychometry, in this dry bulb, DBT, WBT and so on. We have seen the humidity and all. And if you see here in this, we have seen the second law of thermodynamics, and basic properties of the thermodynamics. This we have covered. Now we are here, and in this module 5 we will be seeing the heat transfer, and the second one is the gas compressors. So in my previous lectures we have done this 1 to 4. These things are done, and now I am starting here, and in this heat transfer here, my objective is here. In this heat transfer, I am going to take first Introduction to Heat Transfer, then modes of the heat transfer. In the modes, we will be discussing about conduction, convection and the radiation. So these are the topics which I am going to take in my today's lecture. So if you see the syllabus of this module 5th, it is not 4th, it is the 5th module. So in this we have the basic concept of the heat transfer. In this we have the conduction, convection and the radiation. Then we have the heat exchanger and types of heat exchanger. This is in the heat transfer. And the next is the basic concept of gas compressors, air compressor, single stage reciprocating air compressor, multi-stage compressor, volumetric efficiency, air motors, and the rotary compressor. This I will be discussing in my lecture number 8 or 9th in this about the gas compressor, and 1 to 7 we will be discussing about heat transfer. In the next 10 lectures we are going to dedicate for this module. Now, introduction to heat transfer. You know that every thermodynamic machine or any thermodynamic equipment where heat is added, by this addition of the heat, work is produced. Like power plant, your automobile engines, turbines, and these are used in different types of devices like aircraft, automobiles, power plants to generate the power, and so on. So how much percentage of the heat we are giving and how much we are getting out, they are not the same. If you put the 100% of the heat, 100% work will not be getting. There will be some losses, and these losses, if you divide the output by the input, you will get the efficiency, and we have seen that efficiency has never been 100%. There are some losses due to entropy, due to friction, due to the irreversibility processes which are happening in the system. We are not able to get the 100% efficiency. So how we can get? So how this heat transfers, and this is happening due to the unknown heat transfer systems. So how much heat transfer we are going to take, and also these things are used for cooling, for the air conditioner. We need some radiator, we need some heat exchanger, and also the compressors and turbines, the heat is transferred. So how much heat we should transfer? Because if you see the turbines material are not able to sustain very high temperature because the rotation of this turbines is very big, and due to this rotation, the lot of centrifugal force which is acting and it is pulling out. Due to this pulling out at a high temperature, the material will fail before its ultimate strength. So the temperatures material has to be designed so that it can sustain the very fluctuating load, the flutter load, and other types of load at a high temperature. So we need the cooling of the turbine. If you don't cool the turbine, because the turbines are working continuously. If you see the reciprocating engine or automobile engine, they are not working continuously. Out of 4 stroke, there is a 1 power stroke. In that only heat is given. But in the turbine, it is a continuous process. It is running, and every time it is in the same load. So we need to cool the turbine. Same way, we also need to cool the engine. Also, you might have seen that the diesel engines are cooled by the water, or some coolants are used, and it is going through the radiator. But if you see the 2-stroke and 4-stroke small engines, petrol engine or SI engine, they are air cooled. So there are some fins. These fins are to be added. So more heat transfer will take place and engine will be cooled. Such type of cases we are going to study in this heat transfer. It is very useful for mechanical and aeronautical engineering to design the propulsion system, to design the air conditioner system, and other systems also wherever there is some transfer of heat is persisting. So I am going to give some introduction about heat transfer. So we have defined heat as the form of energy that can be transferred from one system to another as a result of temperature difference. A thermodynamic analysis is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another equilibrium state. So what is the heat? Heat is the form of energy that can be transferred from one system to another as a result of temperature difference. So transfer will take from high temperature, high T to low T. So that is the first thing, and it is a heat transfer, and the direction will be in this way. A thermodynamic analysis is concerned with the amount of heat transfer. So how much amount of heat is transferred? Amount of heat transferred. That is very much essential to find out, that how much heat is to be transferred and it is reaching to the equilibrium state. The science that deals with the determination of rates of such energy transfer is the heat transfer. So in this we will be discussing the rates, how much per unit time is transferred from one point to the another point is called the heat transfer. So it is a science that deal with the determination of the rates of such energy transfer is the heat transfer. The transfer of energy as heat is always from the higher temperature to medium to lower. So if you see here in this, so it is a high temperature here. So it is high, and here if you see it is a medium, and here it is a low. So medium, and it is the low temperature. So it is moving from this to this. Heat transfer stops when the two medium such as same temperature. So if it will reach, if this temperature high is reaching in the same temperature here, it will stop here. So heat transfer will be stopped when the both temperatures from higher to lower are in the equilibrium, then the heat transfer will stop. Modes of heat transfer we will be discussing about today's lecture. That is we have basically three modes of heat transfer, that is the conduction, convection and the radiation. These are the three modes which we are going to discuss in my today's lecture. So here we will see the modes of heat transfer. First we will see the conduction. So what is the conduction? Conduction mostly happen in the solid slabs. So if you heat the solid slab, it will move from high end to the high temperature end to the low temperature end. So conduction is the transfer of energy from the more energetic particle, means more high temperature particle of a substance, to the adjacent less energetic ones as a result of interaction between the particles. So if you see that there is a slab, this is the slab, this slab, this is the T1 and this is the T2. So if this is T1 is higher than T2, so the energy will transfer from this side to this side. Until the time both the faces are, this is the surface 1 and this is the surface 2. So as and when the transfer will move always from higher temperature to the low temperature. Conduction can take place in solids, liquid and the gases. So this conduction will take place in solid, liquid and gases also. In gases and the liquid, conduction is due to the collision of and diffusion of the molecules during the random motion. So in the gases and the liquid, it is the collision of the molecules, but in this solid, it is by the vibration of the system it is happening. In solid, it is due to the combination of vibration. You see, they are not moving, the particles are there, but due to the high temperature, they start vibrating, very fast vibrating, and due to this vibration, the energies transfer from one molecules, from higher molecules towards the lower molecule energy area. So the molecules, so in solids, it is due to the combination of vibrations of the molecules in a lattice and the energy transport by the free electrons. So in this, what happened in solid, how it is happening? The energy transfer is taking place like this. These are the molecules. These molecules, if you give here some heat, hot source in this zone, you are giving, so what will happen? These molecules, the initial molecules will take this heat from there and their temperature will increase. Due to this increase of the temperature, they will start vibrating like this, and it will due to next, and it will start vibrating, then it will Q to the next, then it will start vibrating. Like this, every molecules will start vibrating and the heat transfer will take place, but they are not moving from each other. They will maintain their location. Location will not change. That is in solid, the molecules will be fixed in their axis and only the vibration will take place, and due to the hot or addition of the heat, more vibration will be there and they will transfer this vibration and the heat to the next, and like this the heat will transfer from one place to the another place. A cold can drink in a warm room. If you put, for example, eventually warms up to the room temperature. So if you take a cold drink bottle and you are removing from the fridge and you are keeping on the surface, if you see that after some time your inside the cold drink will be equal to the same temperature as of the room temperature. As a result of heat transfer from the room to the drink through the aluminum can be by the conduction. So here liquid is there inside the cold drink. So this is the cold drink bottle. Here is your liquid and this is the aluminum foil. So this temperature is here cool. So heat will go from atmosphere and by this aluminum this temperature will be made the equilibrium as the temperature of the room. So rate of heat conduction. So how the rate of heat conduction is depend upon the geometry of the medium, its thickness, materials of the medium and temperature difference across the medium. So if you see in this example, geometry. So what is the geometry of this bottle? That is the geometry of this medium. Its thickness. So how much thickness is there? This aluminum. How much? This is the thickness of the. So it is the thickness. Then material. It is aluminum or anything. So this material is also very important. Which material is more heat transferring? That if you use very fast, this work will be done. And the temperature difference. It is outside room. It is 35 degree and here it is 2 degree. So heat will go from this side to this side till the time here you are not getting a 35 degree centigrade. So like this, they are the 4 parameters. That is the geometry of the medium, its thickness, material of the medium, temperature difference across the medium. These are the 4 parameters which are affecting the heat conduction, and by virtue of these qualities, the heat transfer may be high or less. Rate of heat conduction. How we have to see the rate of heat conduction? You can see this diagram. Here the surface 1, it is the temperature is T1 and another surface is the T2. Area of this A and the distance from here to here is delta X. So this is a slab. So it is shown with some material of the quality. So here experiment have shown that the rate of heat transfer, that is called the Q dot here, through the wall is doubled when the temperature difference, that is delta T, across the wall or the area A normal to the direction of the heat transfer is doubled. So if what it is telling that the Q dot will be 2 times if delta T is 2 times. So thus we conclude that the rate of heat conduction through a plane layer is proportional to the temperature difference across the layer and the heat transfer area. So this heat transfer is directly proportional to the temperature difference, that is delta T, and also area of the surface, but is inversely proportional to the thickness of the layer X. So here the thickness is X. So it is, so I can write here that Q dot is directly proportional to delta T, directly proportional to the A, and also it is inversely proportional to the delta X, that is the thickness. So this we can write, rate of heat conduction is directly proportional to the area A, temperature difference delta T, and it is inversely proportional to the thickness. So here thickness is delta X, this is the delta T, and this area is A. So we can write that Q dot of conduction is equal to Ka T1 minus T2 by delta X. We can also write that minus Ka delta T by delta X. This minus shows that it is towards the high temperature to low temperature. Means it is towards the low temperature. That is why the minus sign is presented here. So it is minus indicates that the Q dot is from high temperature to low temperature. That indicates the minus sign. Here K is the property that is called the thermal conductivity, which is a measure of the ability of a material to conduct heat. So this K is called the thermal conductivity. K is thermal conductivity, and which indicates that how ability of the material to transfer heat. So that is called the K, and this K will be used every time. So K here indicates that it is the thermal conductivity, and which is the measure of ability of a material to conduct the heat. Now we will see here again. So here we can see that if in this limiting case, if delta X tend to 0, the equation reduces to the differential form. Okay, so the same equation we can write, it is Q dot of the conduction is equal to minus Ka dt by dx when X extend to 0 limit, then this delta X is equal to dx, and delta this T2 minus T1 or T1 minus T2 is equal to delta T. So we can write it as a rate of heat transfer Q dot is equal to minus Ka dt by dx. Here this dt by dx is the temperature gradient. This part here is called the temperature gradient, which is the slope of the temperature curve on Tx diagram, the rate of change of temperature with respect to the X. And you know that X is the thickness and T is the temperature gradient at location X. Here area A is always normal to the surface. Just area we have to understand that if it is moving from this direction to this area is your this area is your width into this height. This area you have to take, not this L. L will not be there. So always the perpendicular to the direction of the heat transfer area is always taken. So minus sign ensures that heat transfer in the positive X direction is a positive quantity. So we have to see that minus sign ensures that the heat transfer in the positive X direction is always positive. So here this you can see that here it is a 30 degree centigrade and here is the 20 degree centigrade. So this will, if the area is 1 meter, and here it is a copper which is having K is equal to 401 watt per meter degree centigrade. So Q, if you put in this, you will get 4010 watt per meter square. And if your another material is there, it is called the silicon. K is equal to 148, then this heat transfer will be less. Here it is 4010 and here you have the 1480 by the same thickness, but the material is different. So this K matters. So how much you have the K, that is depend upon, and in this way so we have this equation of heat transfer. The rate of heat transfer is equal to minus Ka dt by dx. So this we have understood as of now, which is called the Fourier's law of heat conduction. This is called Fourier's law of heat conduction. So we will see one small numerical on this topic. So the roof of an electrical heated home is 6 meter long, 8 meter wide. So this you can see one house is there. So this is the 6 meter long and 8 meter wide and 0.25 meter thickness. So this thickness of this roof is given 0.25 meter. Flat layer of concrete whose thermal conductivity K is 0.8 watt per meter degree centigrade, figure below. The temperature of the inner and the outer surface of the roof one night are measured to be 15 degree centigrade and 4 degree centigrade. So temperature of the upper surface is 4 degree centigrade and the lower inside the room is 15 degree centigrade for a period of 10 hours. So we have seen it is for the 10 hours this temperature has to be maintained. Determine the rate of heat lost through the roof that night. So how much heat is lost from 15 to 4 degree for 10 hours. The cost of that heat loss to the homeowner if the cost of electricity is rupees 100 per kilowatt. So this we have to solve this problem and find out how much cost is involved for this system of this owner of this house. So we will use the same formula of Fourier's heat transfer and then we will see how it is happening. So just we will go about this. The inner and the outer surface of the flat concrete roof of an electrical heated home are maintained at a specified temperature during a night. The heat loss through the roof and its cost that night are to be determined. So these two things we have to determine. The thermal conductivity K of the roof is given by 0.8 watt per meter degree centigrade. So we will first find out the heat transfer, that is the heat transfer rate, that is the Q dot, and noting that heat transfer through the roof is by conduction and the area of the roof is A is equal to 6 meter into 8 meter, that is 48 meter square. It is perpendicular. If you see the previous diagram, so here it is going from here to here. So area will be this whole area. So it is 6 into 4, not this 6 into 0.25 or 8 into 0.25. So perpendicular to the roof we have to find out. So here area is 6 into 8, it is equal to 48 meter square and the steady state rate of heat transfer through the roof is equal to minus Ka T1 minus T2 by L. So K is given 0.8, area is 48 meter square and here 15 from the inside and minus 4 and divided by 0.25 meter. So you will get 1690 watt. This can be divided by 1000 to it will be 1.69 kilowatt. So this much heat is to be transferred. Now we have to find out the cost of this. So the amount of heat lost through the roof during a 10-hour period and its cost is. So heat Q is equal to, you know that Q dot is equal to Q by T, and this is the time. So here Q is equal to Q dot into delta T. Q dot we got 1.69 kilowatt into 10 hour. So we will get here 16.9 kilowatt hour. And we know that the cost, that amount of energy into unit cost of energy. So unit cost is rupees 100 per kilowatt hour. So we got here 16.9 into 100. So 16,900 rupees we have to spend on this given system. So in this way we can find out that how much energy we have to use to make our room hot during the winter. If the outside condition is 4 degree and we want to maintain our room temperature as 15 degrees centigrade, so we need for 10 hours of the given room, we need the 16,900 rupees if the cost of your is 100 rupees per kilowatt hour. So now we will discuss about another topic which is called the thermal conductivity. So we have seen this Fourier equation that Q dot is equal to minus Ka delta T by delta X. So what is the K? K is a thermal conductivity and is a measure of a material's ability to conduct heat. How smoothly it is able to conduct this heat. For example, if K is equal to 0.607 watt per meter degree centigrade for water and K for is equal to 80.2 watt per meter degree centigrade for the iron at room temperature. So these are the, so water having the less conductivity than the iron or the copper or the gold, which indicates that iron conducts heat more than 100 times faster than the water can. So K indicates that how much times your conductivity of the material is. So in this example, if you see the K is 0.607 and the for iron it is 80.2. So iron has got more than 100% or 100 times faster than the water can transfer. Thus we say that water is a poor heat conductor relative to the iron, although water is an excellent medium to store thermal energy. So storing capacity is different, that we will be discussing in due course of time, but the heat transfer capacity is different, and so water is a poor heat conductor than the iron or copper or the silver or the brass, but water can sustain and accumulate more energy. That is why we use the water for our boilers, for other activities. Thermal conductivity of a material can be defined as the rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. So this is the definition of the thermal conductivity. K can be defined as the rate of heat transfer, that is the Q dot, for per unit thickness, that is delta X per unit meter, and the material per unit as per unit temperature difference. So per unit temperature difference delta T, and per unit this thickness of the material, that is the delta X, how much heat is transferred, that is called the thermal conductivity. The thermal conductivity of a material is a measure of the ability of the material to conduct the heat. So it is the, if your K is high, means your material is going to very fast, thermal conductivity will take place, or the heat transfer will be faster. A high value of thermal conductivity indicates that the material is a good heat conductor. A low value indicates that the material is poor heat conductor or it is insulator. If the value of K is very low, it means it is a insulator, not the heat conductor. So here I want to show some thermal conductivity of the some common materials which we use normally in our day-to-day life. The thermal conductivity of a pure copper at room temperature is 404,401 watt per meter degree centigrade, which indicates that a 1 meter thickness copper wall will conduct heat at a rate of 401 watt per meter square area per degree centigrade temperature difference across the wall. So that is the meaning of this number. And here I have shown some thermal conductivity of some materials at room temperature. So diamond has got very big, that is 2300, silver is 429, copper is 401, gold is 317, aluminum is 237, iron is 80.2, mercury is 8.54, glass is 0.78, brick is 0.72, water is 0.607, human skin is 0.37, wood is 0.12, helium is 0.152, soft rubber is 0.13, glass fiber is 0.043, air is 0.026, and urethane rigid foam is 0.026. So this is the source from where we have taken. So these are the few materials. So here we can see that diamond is very high, after the silver, copper, gold, and if you see the air and all, they are very less conductivity. So conductivity in air, it is very, very minimum. So these numbers are shown so that we can understand that which material has got more conductivity. Range of thermal conductivity, this we can start from here, from the gases. It is a hydrogen or helium, then air, carbon dioxide, they have in the range of 0.1. Then we have the insulator, that is the fibers, wood and foam, they are the insulator, their conductivity is less than 1. Then if you go for the liquid, mercury, then water and the oils have the very less, then water, then we have the mercury. Then we have the non-metallic solids like oxides, rock, food, rubber and all, they have nearly somewhere here. If you see the metal alloys, the aluminum alloys, bronze, steel and the nickel, they have nearly 100. Pure metals like silver, copper, iron and manganese, they have their range is starting from here to nearly 400 and 500. And this diamond is the highest, and they are the crystalline. Diamond, graphite, silicon carbide, beryllium oxide and quartz. So their range is mentioned in this diagram, and by that we can find out that which material has got better conductivity and in which location we have to use which type of material. So our requirement as per the system, we have to choose the material from here, and accordingly we have to select the material as per the application of the system. Mechanism for heat conduction. So okay, we will see for here in solids, we have here solids, liquid and the gas. So first we have shown here the solids. In solids, heat conduction is due to the two effects, the lattice vibrational wave. So in the solid, first is the lattice vibrational waves by its quartz or by its structure induced by the vibration motions of the molecules position at relatively fixed position in a periodic manner called a lattice, and the energy transported via the free flow of electron in the solid. So here we have the two methods. One is by the lattice method, by the lattice wave. Another is by the energy transported by free electrons. These two ways are there by which the energy is transferred in the solids. So if you see here the liquid, in the liquid there are molecular collision between these molecules, and then molecular diffusion. So in the liquid, we have the molecular collision and the molecular diffusion. And if you see the gases, in the gases, it is by the molecular collision and the molecular diffusion. So in the liquid and the gases, both are nearly same, but in the solid, it is not the same. It is by the lattice wave and electronic flow of the free electrons from one part to the another. So this is the two way in which the solid will transfer its heat from one part to the another part. So in the next class, we are going to discuss about convection, mathematical expression, and the numerical. And then we will see the radiation of due to Stephen Boltzmann law, black body, emissivity, absorptivity, and the Kirchhoff's law. This we are going to discuss. This is the reference which I have taken, and this most of these things I have taken from the Eunice Senegal, Introduction to Thermodynamics and Heat Transfer, second edition, McGraw-Hill's. Thank you very much for watching. Any questions, you are welcome to ask. And my email is ydwedi, DWIVEDI @gmail.com. Please do like and subscribe this channel and also give a comment. Till then, goodbye and see you. Please watch my next lecture very soon. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.